Hey everybody, it's Mrs. Cat, and I was sitting here alone in my Zoom room this morning, and I figured while I was here, I would go ahead and record a short video of some periodic trends review. So Mr. Sharkey put this review together. I'm just going to walk through this so we can talk about some of these things with periodic trends. So we've got three different substances, two ions, aluminum ion, which is +3 ion, sulfide ion, which is -2 ion, and a sulfur atom. And what we want to do is rank these from smallest to largest radius. In order to do this, we have to start by filling out our Rutherford-Bohr diagram. So I'm going to use my periodic table with electron shell to help me out with this. I'm actually going to go ahead and start with my sulfur atom and get that nice neutral atom to start out with, and then we'll talk about what to do with the ions. So if I find sulfur, my periodic table, I see that it has 16 protons in its nucleus. Because it's neutral, that also means it's going to have 16 electrons. I'm going to choose a different color to help these stand out a little bit better. So we're going to start with 2 electrons in the first energy level. We're going to have 8 electrons in the second energy level. And then our third energy level is going to have 6 electrons. Okay. This also tells us that we have 6 valence electrons for sulfur. Whoops, can't see that, can you? 6 valence electrons. If we were to do a Lewis dot diagram for sulfur, we would show that by putting our 6 electrons with 1 on each side before we pair up the last 2. Okay, because the sulfur atom and sulfur ion are related by just a change in number of electrons, let's go to that one next. So because sulfide is a form of sulfur, we know that it's going to also have 16 protons in the nucleus. The -2 charge means that we gain 2 electrons. Okay. Anytime you form an ion, we're going to gain or lose electrons from the valence shell. So this means that those 2 electrons are going to be added into the third energy level for our sulfide ion. So 2 electrons in the first energy level, 8 in the second energy level still. Our third energy level with the addition of the 2 electrons will now also have 8. Okay, moving on to aluminum. Okay, find aluminum on the periodic table. It has 13 protons in its nucleus, okay, which means this aluminum atom is going to have 13 electrons, right? If we have a +3 charge, that means we lose 3 electrons, okay? So what I'm going to do is I'm going to start out with the aluminum atom's electron arrangement, and then I will adjust my number of electrons from there. Okay, so 2 electrons in the first energy level, 8 electrons in the third, 8 electrons in the second, 3 electrons in the third energy level. That is for the atom. Those are the 3 electrons that we are going to remove. So I'm going to go ahead and just erase those. So we're going to wind up with 2 electrons in the first, 8 electrons in the second. Okay, I want you to take a minute here before we go ahead and rank these and look at these valence electrons for the 2 ions. Notice that they both have 8 valence electrons in the outer shell. Okay, that is what we are going for when we form ions or create bonds, is having 8 electrons in that outermost valence shell. Okay, there are some exceptions. Our smaller atoms of hydrogen and helium, they would have a full valence shell with just 2 electrons. Okay, everything else, the goal for valence electrons is to get to 8. Okay, let's take a look at these and rank them based on smallest to largest. Okay, here's what we want to always think about with periodic trends. 2 things, and these are both related to attractive force. Okay, first thing is the number of energy levels that your atom has or ion has because that's going to give us an idea of the distance from the nucleus that our valence electrons are going to be. Okay, distance and attractive force are related inversely, which means as distance from the nucleus increases, attractive force is going to decrease. Okay. Second thing we want to look at is number of protons in the nucleus. As we increase the number of protons in the nucleus, we're going to increase attractive force, okay, which is going to affect all of our periodic trends. So first thing I notice here when I'm looking at these is that I have, oh, I don't like that color, is that I have the aluminum ion has electrons that just go in the second energy level, while sulfur and sulfide have electrons in the third energy level. That's going to make that aluminum, actually, if I just go ahead and highlight that, okay, let's do it this way. Just by the placement of the electrons, we can see that the aluminum ion is going to be the smallest because it has fewer energy levels. Okay, energy levels, electron shells, we can use those interchangeably. Okay, so I'm going to go ahead and take a look just at sulfide and sulfur. So let's zoom in on these a little bit. Okay, these have electrons in the same energy levels, first, second, and third. The other thing to pay attention to is that number of protons in the nucleus. Okay, 16, 16. Those are both the same as well. So we have to look for the difference between these. Okay, I'm going to go ahead and erase these pink rings, okay, because the difference here is in the number of electrons in the outermost shell. Okay, sulfide has 8, sulfur has 6. Okay. What do we know about electrons? Well, they're really small and they have a negative charge. Okay. The negative charge is what's important here. That's going to give us an idea of what's going to happen when we add in those extra 2 electrons in the outermost shell. Negative charges and other negative charges are going to repel each other. So what happens is when we add in more electrons, we're going to have more repulsion between them. That's going to make our sulfide ion larger than the sulfur atom. Okay. You're only going to look at the number of electrons in the outermost shell if everything else is identical, just like we have here. Okay, really what this is only ever going to be something that you look at when you are comparing an atom to its negatively charged ion. That's the only time you're going to look at the number of electrons in the outermost shell to tell you the difference between the atomic or ionic radii. Okay, any other time, you're going to have a difference in number of energy levels or number of protons in the nucleus, and that's where you want to focus. Okay, so again, always about attractive force. Let's take a look. Oh, I guess I can go ahead and put these in here. Sulfur, sulfide is going to be the largest, and then we've already got our reasoning down here. Okay, let's take a look at another example. This time, let's take a look at hydrogen, nitrogen, and fluorine, and we're going to rank these based on electronegativity. Okay, so hydrogen has 1 proton in its nucleus, and its 1 electron is going to go in the first energy level. Nitrogen has 7 protons in its nucleus, 2 electrons in the first energy level, 5 electrons in the second. Okay. And then fluorine, 9 protons in its nucleus, and it's going to have 2 electrons in the first energy level and 7 electrons in the second. Again, we're going to use our periodic table with electron shells to help us figure out those electron arrangements. Okay, electronegativity is the ability for an atom's nucleus to attract electrons from another atom. Okay, so again, trends are always about attraction. So we've got to talk about size or number of energy levels, and we also have to talk about protons in the nucleus. So let's check out those things. Let's look at size or number of energy levels first. Okay. So I'm going to kind of do the same thing as I did before. I used pink, didn't I? So there's our valence shell of electrons for hydrogen. There's for nitrogen, and there's for fluorine. Okay, so hydrogen is the smallest because it's only got electrons in the first energy level. Nitrogen and fluorine both have electrons in the first and second energy level. Okay, now here's the catch with this. When you're ranking things with electronegativities, use your resources to help you out, which your other periodic table that you have, okay, we're periodic table with ions, okay, you've got electronegativity values on this. So I'm going to use this to help us out because if you rank electronegativity of atoms incorrectly, myself and the other chemistry teachers are going to be a little frustrated because you do have that information. I'm going to go ahead and look these values up. Hydrogen is 2.1 for its electronegativity, nitrogen 3.0, and fluorine 4.0. So these are actually in the correct order already. So I'm going to go ahead and place these here, and then we'll talk about the reasons why. Okay, so we can obviously see that we have a difference in the number of energy levels. You would think that because hydrogen is smaller and its electrons are closer to the nucleus, that it's going to have a greater force of attraction for other atoms' electrons because they can get closer to the nucleus. The catch with this is that there's only one proton in that nucleus, and so it doesn't have a very strong force of attraction. Okay, so let's make a note of this. Only one proton, therefore weak attraction. Even though electrons are close to the nucleus. Okay, so that's the reason that hydrogen is going to be the smallest as far as electronegativity is concerned. Okay, nitrogen versus fluorine. Let's zoom in, take a little closer look. Again, these are both going to have electrons in the first and second energy levels, so the distance from the nucleus for those electrons and the electrons that are coming in from another atom are going to be pretty close, right? So here we've got to look at the number of protons in the nucleus, okay? 7 protons for nitrogen versus 9 protons for fluorine. So we've got 2 extra protons in the nucleus, which is going to give fluorine 2 more protons, therefore a stronger force of attraction for electrons. That means the electronegativity is higher, okay? Fluorine actually has the highest electronegativity of all the atoms on the periodic table because of this. It's relatively small in size, and it's got a large number of protons in the nucleus for that size, so it is really attractive for those other electrons in atoms that it might bond with. Okay, so it's a nice summary and review of our periodic trends. These, again, regardless of what trend you're looking at, radius, ionization energy, electronegativity, the reason behind these trends all have to do with the attractive force for electrons from the nucleus. Okay, the 2 factors that we have for that attractive force are going to be distance from the nucleus, which is related to the number of energy levels, and the number of protons in the nucleus, okay? As distance from the nucleus increases, attractive force decreases. As number of protons in the nucleus increases, attractive force increases, okay? So make sure you're always using those 2 things to explain your periodic trends. If you have any questions, make sure you reach out to me or your own chemistry teacher, and I hope you have a great afternoon or day, morning, who knows when you're watching this. Have a great time.